All right, we're good. Good morning, everybody. Thanks for being here. My name is Patty Carroll. I'm a senior sustainability strategist at AWS, and I'm joined today by my colleague, Bishesh Adhikari.
Hi, everyone. My name is Bishesh Adhikari. I'm a machine learning prototyping solutions architect at AWS.
And we're going to kind of trade back and forth here over the course of the next hour. Today's session, just to make sure you're in the right place, is about utilizing sustainability data at scale. And if you read the abstract, the focus is really around use cases related to sustainable agriculture and food security. Where's my clicker? I have a clicker. All right, to start out, we'll talk about the scale of some of the problems facing the future of food on this planet, and challenges in effectively leveraging data at scale to solve them. I'll pass it off to Bishesh to walk you through some architecture patterns on AWS for common use cases in digital agriculture. And then we'll share several stories from AWS customers who are using big data on AWS to solve problems related to agriculture and food security. So when we talk about the future of food, I want to emphasize that that is inextricably linked to sustainable agriculture. And so we're kind of talking about food and agriculture together. And agriculture, of course, is how we cultivate the earth to meet our most basic needs, not just for food, but for clothing and shelter. And we have to be able to do this sustainably, to meet the needs of the present without compromising the ability of future generations to meet their needs. That is the definition of sustainability in agriculture. The agricultural revolution began over 12,000 years ago when humans transitioned from hunting and gathering to growing crops, and is still the bedrock of how we, as humans, survive and thrive on the planet today. So agriculture and the future of sustainable agriculture, in light of the threats posed by climate change, is absolutely critical. We must find ways to improve efficiencies, accelerate adaptation, and build resilience into these systems. If we take a look at the Earth's surface, only 29% of it is land. And of that, only 71% of it is habitable and not just covered in ice. If we ignore the fact that ice is melting, today, already, half of all of that habitable land is already used for food production. We cannot create more land, but if we look a little bit closer, we see that only 23% of the land produces over 80% of all human calories and over 60% of protein. So there's a lot of room here for improving efficiencies. Considering another perspective, food production alone is responsible for over a quarter of all global greenhouse gas emissions, which are driving climate change. And less than 20% of that is actually related to supply chain, the transportation, the processing, the retail. The majority is actually in the land use and the growing of crops and the raising of livestock. So we have a bit of a paradox here. Agriculture is a significant driver of emissions. Emissions drive climate change. Climate change poses a threat to the future of crop productivity and food security. So the problem is, how do we do more with less? Less everything. Less land per person as the population continues to grow. Less water as water scarcity becomes an increasing issue in more regions. Less fertilizer. Fertilizer itself is a primary source of greenhouse gas emissions. Less energy. We have to lessen or reduce the impact on the environment, including greenhouse gas emissions. We are dealing with less predictable weather patterns and more weather extremes due to climate change. And overall, we have to reduce the risk of climate change to people and to our planet. So where do we even start? I'm going to say for today that we start with data. Data is information, and information gives us the power to address these global sustainability challenges. But there are a lot of complications in effectively finding, accessing, and utilizing this data. The volumes of data are growing exponentially. Data is coming from new sources all the time, and old sources that are suddenly new again. It's raw, it's derived, there's different types, different data models, varying quality and completeness that's not always transparent. And it has to be used by an increasingly diverse user base, both individual users, different analytics tools, and is being processed and analyzed by more applications as well. So data itself poses many challenges to leveraging sustainability data at scale. And when we talk about sustainability data, we're really just talking about data layers and data sets that are critical to understanding and mitigating climate change, environmental degradation, and risks to the environment and social constructs of the Earth. The Amazon Sustainability Data Initiative is a program that aims to increase access and usability of these types of data sets on AWS. ASDI works with scientific organizations like NOAA and NASA in the UK Met Office and provides cloud grants and cloud credits to help optimize, and the expertise to help optimize and host these data sets on the AWS cloud. They are publicly available to anybody, and they're free in the Open Data Registry on AWS. So they're easy to find and query, and you can now access them and query for them through the AWS Data Exchange and our marketplace. So there's a single API interface for users on AWS to query what data is available, what data is coming from the Amazon Sustainability Data Initiative, what's free, and we also have a marketplace that provides free and proprietary licensable data sets for sustainability use cases. So accessing these types of big data resources in an efficient way in the cloud is only one piece of the puzzle. I presented many data challenges, and there's many more challenges to overcome. I'll hand it over to Vishesh to talk a bit more and go a little bit deeper on solutions to integrate and manage data from many different sources and how we can utilize that data to accelerate sustainable agriculture.
Thank you, buddy. Yeah, thank you, buddy. So let's see how we can use different sources of data and build solutions around it. So there is a main challenge here. The challenge is to combine different sources effectively. And there's also a problem because the old way of handling data does not work anymore, given the challenges that we just saw. And the main reason is data silos. So customers have accumulated a lot of data over the last number of years, and most of that is stuck in data silos. And data silos cause multiple problems. Let's see a few of them. So the first one is it's really hard to do any analytics. Data is split in silos, so it is inaccessible. Copying data from one silo to another takes a lot of time and is not cost effective. And the silo where data sits may also not fit the best price performance required for the workload. And finally, each silo has its own security, management, and access authorization process, which increase operational risk and cost. So what do customers need instead? They need a scalable, secure, flexible data store, which can handle extremely large amount of data. They want to be able to tag catalog data so that it can be searched easily. They want to run multiple analytics tools to ensure they have the right tool for the right job. They also want to move data in all directions between the data lake and the service. So from inside out to outside in and around the outside. They also want a simplified governance around securing, managing, and monitoring data access. And finally, they need all these features with a low cost without compromising performance or scale. So the solution is to move to the modern data architecture on AWS, and this fulfills the 5 needs we just mentioned. And you would see we are making a lot of purpose-built data services here, and that is because we believe there's no single tool to solve all the big data needs. So let's see how it works in practice. So data is centrally located in our data store in Amazon S3. Data can move between services with AWS Glue. Data is also stored in purpose-built databases, for example, Amazon DynamoDB or Amazon Aurora. We can run multiple analytics like Amazon Elastic MapReduce, Amazon OpenSearch Service, or Amazon Redshift. And finally, if we want to go beyond analytics and do machine learning, then we can use Amazon SageMaker. Let's now see how we can architect agriculture solutions on AWS. And whenever we design solutions around data, we have typically these 4 steps. So we start by ingesting the raw data. We then transform it. Next, we apply machine learning. And then machine learning to find insights. And finally, we act on those insights and we make decisions. Let's briefly explore some of the AWS technologies and services that falls in each of these categories. Let's start with data ingestion. So the goal here is to bring data together in a central location in our data lake. And there are a lot of options possible. I'm only going to mention a few here which are relevant to sustainable agriculture. So if we are interested in bringing IoT data from edge devices, from sensors, or from industrial equipments, we would be using services from AWS IoT. If we have streaming data that is coming from sensor devices, we will be landing those with Kinesis Firehose directly into S3. For on-prem data like logs, databases, videos, satellite imagery, we can move them online using AWS Data Sync. But if the data is too big to move over the internet, we can move them physically using AWS Snow Family services. So the idea here is that you rent a device from AWS, you upload your data, and the data is moved back securely to AWS on your account. And that device can range from a very small box to a large truck, which is capable of moving hundreds of petabytes worth of data. And we also have a third source of data, which is already on the cloud. As mentioned by Patty, we have Amazon AWS Open Data, which has a large set of data, including satellite imagery, climate data. You also have other data, private data or paid data that you acquired through AWS Data Exchange. And these 2 sources are already on the cloud. So with these 2 sources, they remove the effort of migrating, maintaining, and organizing data from all the parties. So this accelerates the pace of innovation and research, and it is a more sustainable practice because you don't have to duplicate the data anymore. You don't have to use excess compute to process these data anymore. And finally, it helps to reduce the carbon footprint from everyone. For data transformation in batch or in real time, we again have different options. For example, if we are interested in querying semi-structured data using SQL, we have Amazon Athena, which we can use to query a very large amount of data without having to think about clusters or servers. So it is a serverless option. And what you need to do is you just need to point to the data, you define the schema, and you can start querying. So for example, you could use Amazon Athena to query AWS Open Data, and analyze 200 years worth of global climate data. If you are interested in petabyte data processing using open source frameworks like Spark, Presto, or Hive, then you would use Amazon Elastic MapReduce. If you are interested in just performing ETL, so extract, transform, and load, in a serverless fashion, then you would use AWS Glue. And finally, if you want to do analytics on streaming data, then you would use Kinesis Data Analytics. So an example here is you can use Kinesis Data Analytics to detect any anomalies coming from your sensors in real time. So next, for machine learning, AWS offers the most complete set of AI and ML services to meet your business needs. And we have mainly two categories of offering here. The first one is high-level AI services, where you don't need any machine learning experience to use them. It's just an API call. Again, I have listed only a few here, and there are a lot more available. So for example, you can use Amazon Forecast to do time series forecasting. So in agriculture, you could use this to forecast your crop growth or crop failure. We have Amazon Recognition to do computer vision workloads. So you could use this to find diseases or pests on your crop. And we also have Amazon Transcribe, which help you to convert audio to text. So again, in agriculture, you could use this to automatically convert your scouting notes. On the other hand, if you already have a machine learning, a team with machine learning experience, then you would go for Amazon SageMaker, which is our cloud ML platform, and which helps you to build, train, and deploy machine learning models for any use case with fully managed infrastructure, tools, and workflows. Finally, when we have the insights, we can act on those insights. And depending on what you want to do with that, we have, again, different options. So if you are just interested in business intelligence, generating reports, visualizing it, then you would use Amazon QuickSight. If you want to present the insights to your end users through web application or mobile, then you use Amazon CloudFront. You can also distribute those insights through API, and you have purpose-built service like Amazon API Gateway to make it easier. And finally, you can also trigger actions automatically and act on and make decisions. So you can use services like AWS Lambda to trigger specific actions. For example, you could irrigate automatically given the condition of the crop or the weather, or you could even send drones for inspection. So taking action produces further data points, and they can again be used as input to other use cases. And this way we close this loop, and architecting this way allows us to continuously improve and make better decisions. So now that we have seen some of the AI services, let's see how we can use them in practice. I'm going to share some agriculture solutions and some demos of it. We will review them first. We'll also see how they are built, and we'll also see the reference architecture for each of them. So I'm going to start with the first use case, which is crop health and growth monitoring. So this demo is going to leverage satellite imagery and weather data to monitor the crop health and the growth. So before I start, there are two notions that are very important in agriculture and also in this demo. The first one is NDVI, so it stands for Normalized Difference Vegetation Index. So it is a satellite-based vegetation index which helps you to know whether your crop is doing well or not. So it gives an idea about the health. So as you can see on the image here, we have the satellite image, and next to it we have the NDVI view. So the NDVI view gives us a clear indication which part of the area is doing well in terms of health and which parts needs our attention or is not doing well. The value of NDVI range from 1 to 0, so the values that are very close to 1 are in the healthy range, and those that are very close to 0 are in the unhealthy range. the next notion we are going to review is GDD. So this stands for growing degree days. And it is a temperature-based index to assess the crop growth. So the idea the idea is that for a crop to move from one stage of development to another, it has to accumulate some amount of energy, and that energy here is temperature. And with GDD, we will have thresholds for each stage of development. For example, you would have a specific threshold when your crop is in vegetative stage, and you will have another one, for example, when your crop reach maturity, for example. So let's look at the demo. So on the demo, we have the satellite view on the left. We'll also have an NDVI view of the field. And on the right, we have two charts. So one is for NDVI, which gives, again, an idea about the health of the crop. And on the dark green to light green, we have the GDD over time. And that gives an idea about where our crop is in terms of the development stage. So as you can see, we are following the evolution of a single field here over time. And on the left, the NDVI image is evolving. And on right, we also have the two values, the GDD and NDVI average value for the field. So this chart here gives a quick idea about what's happening with the field in time. We know exactly what is happening, how it is doing in terms of health, and where it is in terms of development. So how does this demo support sustainable agriculture? This is a form of remote sensing. So it helps to scale farmland monitoring, so you can monitor very large areas. NDVI we used here for a single field, but we can also run NDVI on an entire region. And that way we will find regions that are doing well and regions that have issues. And we can prioritize our physical visit to only those fields or regions which are not doing well. So we can prioritize the local inspection. There is no need to visit all the fields. And with GDD, we will also be able to find when is the optimal time to go and do crop scouting. So going physically and checking whether there is any disease signs or whether there is pest infection. And it also helps us to find the best time to apply fertilizer or pesticide. Let's see how this is built, very high-level reference architecture here. On the top, we have the computation of GDD. So we are using AWS open data. The weather data is coming from NOAA, and it's already in S3 bucket. So we're using AWS Glue to do ETL process. So we're extracting the data for the region of interest. We're computing the GDD, and finally we are saving the data in DynamoDB. On the bottom, we have satellite image from Sentinel-2. They are also available on AWS Open Data, S3 bucket, and it's available freely. And we're using serverless compute here to compute NDVI. And we're presenting on the web, on the application using CloudFront. So key takeaways here. It is easy to get started to do remote sensing on your field or your region of interest. Data is already there. GDD and NDVI are quite easy to compute. And of course, you can take this as baseline and extend this with ground level sensor information, which will give you more frequent monitoring and more precise information about your crop. Let's have a look at the second use case, which is about field boundary detection. So detecting individual field boundary is important to access digital agricultural services and tools. So it's easier to do field level assessment and also monitoring. We can study each field in detail. We can focus on high value crop. We can optimize resource per field. And using field boundary, we can do precision agriculture, precision farming, which allows us to treat each field independently. This means instead of applying same quantity of fertilizer or water to all the fields, we can only focus to treat regions or field that have issue and apply only a specific amount of water or fertilizer. So this is a more sustainable practice, and it minimizes the resource, and it helps to also to optimize the yield. So we are using machine learning here to find the field boundaries automatically. So on the left, we have the satellite image as input. Next, we're using a deep learning model and find the boundaries, as you can see on the right image. They are outlined in white. So once we have these boundaries, we can combine ground level data, field data, like crop type, field area, planting date, treatment we used, nitrogen or water used, and together with indexes like NDVI, we have more data about the field, and we can build together even precise machine learning model, which will be able to help us to find the estimate yield and also to find the optimal time for harvest. Let's see how we can build such a system. So again, we are using Sentinel-2 images. We are extracting only the image that are from our region of interest. We are then using Amazon SageMaker to process the image and then create a machine learning model. The model is saved back in S3, and finally we can use that model to find new boundaries on a new image. And on the right, you have the front-end technologies we are using to display them on the web app. So key takeaways here, data again is already in S3. You can start with this use case, but you can also do more because Sentinel-2 has 13 bands, so you can also imagine other use cases, for example, crop type detection or even do a nitrogen deficiency check. So, and if you are not familiar with machine learning, you can also use high-level AI services, which I mentioned earlier. And SageMaker also has a tool to label the images automatically. So SageMaker Ground Truth helps you to label your images, and then you can use high-level AI service to start with machine learning. And there are also, by the way, pre-trained model or generic model that you could use if you don't have experience with machine learning. So let's see our third use case, which is about crop management system. So if we put everything together, like from satellite imagery, weather data, weather forecast data, ground level data from sensors, and if we use high-level AI services, we can build a custom crop management system. So let's see how the demo works. So this demo will have the two features we just saw, but on top of that, we are adding new machine learning features. So the first one is about machine learning recommendations to farmers. So it can help them to give specific actions to take on their field. And it will look at the current state of the crop, the weather condition, the weather forecast for next 48 hours. So it will look whether it is going to rain or is there high wind, etc. And given these data points, it will be able to recommend whether it's the best time to fertilize, to apply irrigation, or is it already time to harvest. The next machine learning feature we're using is crop growth forecast. So we would be able to predict the crop growth for the next week. So let's have a look quickly. So as I said, it's using the two features we saw earlier, field boundary, NDVI. We have the NDVI over time. Then we have machine learning recommendations. And you can see the recommended actions in green. And on the right, the chart is now showing us a forecast of the crop growth for next week. So why is this kind of solution useful for farmers? So first, it can help you with specific actions that you can take, from simple actions like, when is the best time to apply fertilizer? I mean, if there is wind or heavy rain in the 48 hours, it will recommend you not to do so. But it can also help you notify for other conditions like frost or storm in advance. And in that way, you can, as a farmer, you can take some actions to minimize the damages from these conditions. With the growth and the GDD forecast, again, it can help you to understand whether you will reach, for example, maturity next week. And in that way, you can start preparing for harvest. So you can do this order of harvest. You can also check your equipments if they are working or not. And finally, you can also start preparing for storage. And on top of that, you could also takes some actions automatically, so some decisions. You can irrigate automatically, apply fertilizer as well automatically. So let's again see the reference architecture very quickly. So on the top, you have weather data processing. We are using, data from open data, so AWS open data, so Noah Bucket. So you can use similar approach, so ETL with AWS Glue to process further data points from weather. In the middle, we have computing NDVI. So again, we're taking images from S3. You can also compute other indexes, by the way. You are not limited to NDVI. There are other indexes like EVI or NDWI, water index, moisture index, etc. And on the bottom, we have a machine learning process. So again, we are getting all the image we need for our region of interest, and then using SageMaker to train a model. And as you can see on the top right, we are using high-level AI services here, Amazon Forecast, where we just use an API with our data to be able to predict what's going to happen with the crop growth. And on the right, we have front-end technologies to show the web app. So key takeaways here. You can start with AWS Open Data. There's a lot of data available there. I'm sure you will find one that fits your need. And if you are not experienced with machine learning, you can use high-level AI services. So for example, you could use Amazon Recognition to do different type of machine learning use case, like crop type detection, find disease, find pest infection, etc. And you can also automate some of the actions. So you can send automatically a robot to do harvesting, or you can send a drone to do fertilizing. So in general, satellite imagery are complementing what you have on the ground from your ground level sensors. So it is best to use both of them, because with satellite imagery, you can monitor very large areas remotely. So with this, I'm going to hand over back to Patty. We'll be talking about some customer success stories in sustainable agriculture.
Thank you, Bishash. Excuse me. Okay, so for the next 25 minutes or so, I'm going to walk you through several stories from AWS customers. The first that I'd like to introduce you to is EOS Data Analytics, or EOSDA for short. EOS Data Analytics is a global provider of AI-powered satellite imagery analytics. The company operates worldwide and partners with government, commercial, and scientific organizations. EOSDA provides Earth observation or satellite imagery-based solutions for smart decision-making across 22 industries, but their focus is on agriculture and forestry. And their mission is to harness the power of satellite technologies to provide fast and accurate data-driven decisions. USDA is strongly aligned as a business with 10 of the 17 United Nations Sustainable Development Goals. And they use these as guidelines in developing and prioritizing new solutions. They currently offer 3 satellite-based platform products: crop monitoring for precision agriculture, forest monitoring, more specifically for forest management, and Land Viewer, which allows for on-the-fly searching, visualizing, and processing of satellite data. USDA builds their solutions on AWS, and just recently, just last month, this month, a couple weeks ago, officially joined the AWS Partner Network. They leverage services like EC2, AWS Lambda, S3, Elastic Load Balancing, and Amazon CloudFront. So these 3 core products are designed to address a wide variety of use cases. And I'll share a few of those examples with you now. The first is soil nutrient management, or soil fertility management. Crops need the right nutrients to thrive. Those nutrients mostly come from the soil, soil can be depleted. And there are ways to help preserve, maintain, and restore soil fertility. But the application of fertilizer is still necessary for most crops. Satellite-based productivity zones are illustrated in this diagram here. And it looks a lot like NDVI because it is based on NDVI, which Bishesh introduced. By using this index to zone a field into different levels of productivity, farmers can customize the amount of fertilizer that needs to be applied in any given place. So they don't need to apply the same amount to the whole field, and they don't have to worry about applying too much in areas that don't need it. This is called variable rate application, or VRA for short, for these precision fertilizer application maps. And this is enabled by those productivity zones, but satellite data alone can't tell you exactly what's in the soil, and so you still need soil testing and soil sampling by a lab to understand the actual levels of nitrogen and phosphorus and other nutrients so you know what to add. Soil sampling and testing is really expensive and time-consuming, so these productivity zones can also be used to strategically locate where you're taking samples in the field, reducing the overall number of samples that are needed without sacrificing the accuracy of the analysis. This reduced costs significantly for farmers, so it improves their return on investment, both by reducing those costs, but also by optimizing the yield by applying just enough fertilizer as needed, no more nor less. And by applying just the right amount of fertilizer, this is reducing the potential environmental impacts, including greenhouse gas emissions, from excess fertilizer use. The efficient use of fertilizers is just one aspect of sustainable farming. But these kind of detailed insights into soil fertility and crop productivity, especially in regions that are just coming up to speed with modern technologies for precision agriculture, this is instrumental in helping farmers learn and build more resilient and healthy soils over time. The second use case I want to share is crop classification in Ukraine. Crop classification for monitoring and managing agriculture production in the country of Ukraine. Ukraine is a major breadbasket of the world, so when a crisis like war happens in Ukraine, as I'm sure everybody in this room is familiar with, the global food supply in the region is derailed pretty quickly, and acute food security rises steeply. USDA provides crop classification at regional and country levels in the Ukraine and has been since 2016. These data layers are all available in their crop monitoring platform. They have a proprietary neural net model and have demonstrated over 90% classification accuracy. So accurate and precise crop classification data is critical for governments and businesses to monitor crop production in countries like Ukraine so they can respond rapidly and effectively with the right resources to the right places when that food supply is at risk. The third story from EOSDA I'd like to share is more of a social impact component. This is a more recent project to support inclusive and cooperative natural resource planning in the Republic of Chad. Communities in developing countries like Chad still rely on pastoralism and subsistence farming to survive, to feed their families and their local communities. Approximately 25% of the global population relies on small, local family farms, less than 5 acres, to survive. The challenge in Chad is a decades-long conflict between indigenous pastoralists and local farmers who don't agree on the use of natural resources in the region. So these conflicts are on the rise, and they're rising steeply in Chad due to climate change. In recent years, Chad has experienced devastating flooding and droughts, causing damage to crops, soil degradation, loss of livestock, loss of wildlife and biodiversity, and losses of homes and ways of life. So these pressures, with increasing famine and anxieties around the changing climate, are causing a rise in conflict. EOSDA was enlisted by local indigenous leaders to help support a participatory mapping project. Participatory mapping, if you haven't heard of it, is actually really interesting. It's the creation of maps by local communities that represent and communicate their specific needs and use of the land, including features of cultural significance and importance. The communities can work together to identify disputed areas and the shared resources that they have to negotiate, and then collaborate to develop rules of their use and find compromise. So EOSDA Land Viewer was used to create a printable 2D map layout for the locals to use and to add their information to. It was annotated with natural and artificial objects, so it was ready to go. And there were 24 communities initially participating in this project. That quickly grew to 116 communities, and from an area of 50 to 60 square kilometers to over 2,000 square kilometers. Along with this map, it was supplemented by a written agreement between the communities on how they will use and share natural resources, as well as strategies for future conflict management. For this and the other stories, and for many more, please check out their website, EOSDA's website. There's a lot of great case studies and more detail on each of these projects. So to close it out with EOSDA, I want to tell you about EOSDA, a constellation project. This will be the first agriculture-focused satellite constellation among companies that are utilizing remote sensing technologies. In December of 2022, next month, EOSDA will launch their very first satellite in this constellation into low Earth orbit. What makes it agriculture specific is the unique set of 13 bands that are tuned for farm and crop monitoring. The full constellation of 7 satellites will be in orbit by 2025. And at that point, it will cover 98.5% of all farm and forest lands globally every 5 to 6 days. Daily monitoring is also possible with one-day revisits for targeted areas. And the analytics on the back end mean the data capture to insights available through the platform occurs in under 24 hours. So with that, I want to transition to talking about more of an institution. EOSDA is just getting started, and they have a long way to go. The next customer was founded in 1854. The UK Met Office. Met Office is the National Meteorological Service for the UK. They provide weather, climate, and other environmental data layers, along with the tools and the expertise to help all types of users worldwide access, query, and utilize this data, whether businesses, governments, or scientists. Met Office supports organizations, leaders, and innovators in making both short-term decisions with weather and long-term decisions based on climate change models and simulations. Met Office data support are invaluable to those who are seeking to understand and mitigate the effects of climate change on agriculture and food production. I'd like to share an example of how scientists are using Met Office data. A team of scientists led by Dr. Catherine Bradshaw recently studied the effects of climate change on food security in South Africa. The publication was released just earlier this year, if you'd like to check it out. But the gist of it is that maize production is the most important crop that's grown in South Africa. It is a staple food crop for domestic consumption, and it's also exported for regional consumption as well. Bradshaw and her team leveraged Met Office data to investigate the impact of climate change and climate change extremes, weather extremes, on maize yields in the region. They demonstrated that yields have already been severely reduced due to extreme weather events related to climate change, extreme high temperatures, and low precipitation. They've also shown that record-breaking temperatures in season today are 500% more likely to occur than just 50 years ago. But what does this mean for the future? How will climate change impact future yields and food security? By analyzing climate change simulations, the increasing potential for extreme high temperatures and extreme low precipitation over time becomes evident. And this actually suggests that in the not too distant future, the region will become unsuitable for maize production as it exists today. So based on research like this, it's clear that significant investment is needed, not just in optimizing maize production, but in developing the adaptation strategies that are needed to protect food security in the region in southern Africa. This is just one example of how researchers are leveraging Met Office data at scale to address some of these critical challenges and questions. But our scientists are increasingly weighed down by the technical overhead of the data and of the compute. And that is slowing the pace of science research. So the heart of the problem here is that scientists are constrained by the tooling and the data they have at hand to do their work. These constraints can inadvertently lead to bias in the research results and even encourage researchers to confirm the results they already expect. It stifles the exploration and creativity needed for truly novel scientific discovery. The most important scientific results are usually unexpected. And today, more than ever, we need our scientists to have the right tools for the job. So Met Office is committed to giving scientists back their flow by pioneering a new generation of scalable tools and platforms for scientists with a modern user experience. Modern solutions must also account for the modern ways that researchers work in global collaborations. This geographic separation is one of the root causes of data silos. So you can have users and scientists in one geography using entirely different data sets and tools, or different versions of data sets and tools than in another geography. And that's a problem because these small differences can add up to bigger discrepancies and limit reproducibility and trust in the results. The geographic expanse, of course, also introduces complexities on compute. When you have data located in different regions, the orchestration of that data and the modeling and the analytics that needs to happen on top of it. Users face long, costly, and resource-intensive compute orchestration. So Met Office was seeking to provide scientists around the world with a managed service to efficiently find and utilize the data they need wherever it is, wherever they are. So Met Office teamed up with AWS to try to solve this problem. Climate scientists and technologists began by working together to identify the core needs, generate ideas and brainstorm, and evaluate the opportunity. From there, Met Office and AWS cemented the vision into a press release and PR FAQ, or FAQ document. And the AWS prototyping team was onboarded to help make that vision into a reality. Building a prototype is a crucial step here, not just to prove the concept, but to give the project the ability to fail fast and iterate and really prove the value of the new solution before it is finalized, shipped, and scaled. With the AWS prototyping team and their cloud technology and engineering expertise, they were able to design and deliver the first proof of concept solution for the Met Office in a matter of weeks. So here's a look at the solution's architecture for the prototype. Each of these VPC regions, we have 3, represent a different geographic region. And they're all connected through AWS Transit Gateway. This solution combines several frameworks and technologies, including Dask on AWS, Amazon FSx for Lustre, S3, and ECS. Together, these help orchestrate the distributed petabyte scale compute across the different regions. This solution is innovative for 2 main reasons. First, it provides an efficient, user-friendly way to distribute that compute for data science across various regions, and it enhances big data querying capacity across different regions with purpose-built storage layer that's optimized for read-write between different storage units. So the outcomes of the project aren't just technical specifications. We're only at the prototype stage here. But the implications are big for the scientists and the user experience for those researchers. A primary driver was to help scientists spend more time doing science. And this is achieved by tackling the undifferentiated overhead, the heavy lifting of data and compute management, so that scientists experience improved speed and ease of discovering the data that's available and loading it, the automated distributed compute of large-scale modeling and analytics workloads, and automated orchestration of the compute across different regions globally. From the technical side, with data proximate compute and Amazon FSx for Lustre, this new architecture results in big savings on compute time and energy as well. The team put it to the test on a use case from Dr. Bradshaw's research in modeling corn yield, maize yields in South Africa. And in that test, the compute time was reduced by up to 65%. If all users of Met Office data leverage this solution pattern, the reduction in the data that needs to be transferred between regions also amounts to significant energy savings. It's estimated that it would be the equivalent of powering 40 US-based homes every day. But of course, the most impactful efficiency improvement is in the scientific process. By reinventing the tools that scientists need and use to access and analyze climate data and other environmental data layers at scale, they can achieve and publish new results faster with more reproducibility. And by reducing the time to discover these new insights and disseminate new scientific information, we can accelerate the development of evidence-based strategies to protect global food security. So with that, we invite you to pull out your phones if you don't already have them out and take a picture of this slide. We wanted to provide you with some resources for more information and to get started. If you visit the 4th floor of the Venetian, you can check out the Smart Crops demo and see in action some of the demos that Bishesh was sharing with you today and ask any questions about architectures and how to leverage that. And with that, I'll thank you all for your time for being here instead of the keynote this morning. Feel free to reach out.